Hi everybody, welcome to the second video in the derivatives section of the Calculus Guide video series. In this video we're going to be covering more of the differentiation rules. So here are the differentiation rules that we've covered so far. We've looked at the constant rule, the power rule, the constant multiple rule, the sum rule, and the difference rule. And now we'll cover some more differentiation rules. The sixth rule is the product rule. If u and v are differentiable functions at a point x, then so is their product u times v. The derivative of u times v with respect to x is equal to u dv dx plus v du dx. So that's our product rule. Now here's an example of using the product rule. Say we want to find the derivative of y equals x squared multiplied into, open bracket, x plus 3, close bracket. To do this, we let u equals x squared and we let v equals x plus 3. Our derivative dy dx is equal to the derivative of u times v with respect to x. And using the product rule, that's equal to u dv dx plus v du dx. So our value of u is x squared, our value of dv dx, that's equal to 1. Our value of v is equal to x plus 3, and our value of du dx, that's equal to 2x. And when we multiply that out, we get that our derivative dy dx, that's equal to 3x squared plus 6x. So our seventh rule is the quotient rule. If u and v are differentiable functions at a point x, and if v of x is not equal to 0, then the quotient, u divided by v, is differentiable at x, and the derivative of u divided by v with respect to x is equal to v du dx minus u dv dx, all divided by v squared. So that's our quotient rule. So here's an example of using the quotient rule. Say we want to find the derivative of y equals x squared plus 1, all divided by x squared minus 1. Here we let u equals x squared plus 1, and we let v equals x squared minus 1. So our derivative dy dx is going to be equal to the derivative of u divided by v with respect to x. And using our quotient rule, that'll be equal to v du dx minus u dv dx, all divided by v squared. So our value of v is equal to x squared minus 1. Our value of du dx, that's equal to 2x. Our value of u is equal to x squared plus 1. And our value of dv dx, that's equal to 2x. And our value of v squared, that's equal to, open bracket, x squared minus 1, close bracket, squared. So if we substitute all of those values into our equation for the quotient rule, we get that the derivative dy dx is equal to, open bracket, x squared minus 1, close bracket, 2x, minus, open bracket, x squared plus 1, close bracket, multiplied by 2x, all divided by, open bracket, x squared minus 1, close bracket, squared. And when we multiply that out, that's equal to 2x cubed minus 2x minus 2x cubed minus 2x, all divided by, open bracket, x squared minus 1, close bracket, squared. So our plus 2x cubed and our minus 2x cubed terms cancel, and our minus 2x and our minus 2x terms combine. And we get that our derivative dy dx is equal to minus 4x divided by, open bracket, x squared minus 1, close bracket, squared. So having just looked at an example for the quotient rule, now we're going to look at using the power rule for negative integers. So we looked in a previous video at using the power rule for positive integers, and we're just going to revise that up at the top of the screen here first. If for a function f of x is equal to x raised to the power of n, then our derivative df dx, that's going to be equal to the derivative of x raised to the power of n with respect to x. And according to the power rule, that will be equal to n times x, where x is raised to the power of n minus 1. So in the table at the top of the screen, we have different values of the function f of x. We've got f of x is equal to x, f of x is equal to x squared, f of x is equal to x cubed, and f of x is equal to x to the 4. And in the second row of that top table, we've got the corresponding derivatives. So our derivative of x, that's equal to 1. And the derivative of x squared, according to the power rule, that's 2x. And the derivative of x cubed, according to the power rule, that's 3x squared. And so on. So what we can also do with the power rule is we can use the power rule for negative integers. It's useful to remember that we can express some quotients as a power with a negative integer. For example, the quotient 1 divided by x, that can also be written as x to the power of minus 1. And the quotient 1 over x squared, well, we can write that as x to the power of minus 2 also. If we look at the table at the bottom of the screen, in the first row of that table, we've got different values of f of x. We've got f of x is equal to 1 divided by x, f of x is equal to 1 divided by x squared, and so on. And in the second row of that table, we're rewriting that f of x as x raised to the power of some negative integer. So that 1 over x, we can rewrite that as x to the power of minus 1. That 1 over x squared, we can rewrite that as x to the power of minus 2. That 1 over x cubed, we can rewrite that as x to the power of minus 3, and so on. In the third row of that table, we've got our derivative, df dx. So these derivatives have been calculated not using the quotient rule, but these have actually been calculated using the power rule with a negative integer. So this is a different way of calculating the derivative. We'll apply that in the first example. In the second row, our f of x is equal to x to the power of minus 1. So if we were to apply the power rule to calculate the derivative there, well, f of x is equal to x raised to the power of n, where our n is equal to minus 1. And according to the power rule, our derivative is going to be equal to n x, where x is raised to the power of n minus 1. Now if n is equal to minus 1, then our derivative is equal to minus 1 x raised to the power of minus 1 minus 1 is minus 2. So our derivative becomes minus x raised to the power of minus 2. And we can evaluate the other derivatives in the same way. That minus 2x raised to the power of minus 3, minus 3x raised to the power of minus 4. Now when we look at the bottom row of that bottom table, this is the derivative being rewritten as a quotient. So for that derivative minus x raised to the power of minus 2, we can rewrite that as a quotient, minus 1 over x squared. And that derivative minus 2x raised to the power of minus 3, we can rewrite that as a quotient, minus 2 divided by x cubed. So having looked at an example in our previous screen of using the quotient rule, and then seeing here how we can calculate derivatives of x raised to a negative integer rather than doing it as a quotient, you can see here how using the power rule in these cases involves less work than using the quotient rule. So it's quite useful to remember that we can do this, because you can save yourself a lot of time and effort. In a lot of other cases you will have to use the quotient rule, but in cases like these you can use the power rule. So here's some differentiation rules that we've covered so far. We looked at the constant rule, the power rule, the constant multiple rule, the sum rule, the difference rule, the product rule, and the quotient rule. And we've also looked at instances where we can use the power rule with negative integers rather than the quotient rule in some particular cases. So having looked at these differentiation rules, now we're going to do a comparison between evaluating a derivative from the definition by evaluating a limit versus evaluating the derivative using differentiation rules. And we're going to see that it can be more efficient and less time consuming to use the differentiation rule rather than to evaluate the limit. So here's our example. We want to find an equation for the tangent line to the curve y equals x squared through the point 3, 9. In order to do that, we want to find the slope of the curve at the point 3, 9. And in order to do that, we're going to differentiate y equals x squared at the point 3, 9. So we're going to do that by evaluating the limit at that point. So our slope, represented by variable m, is equal to the limit of the difference quotient f of x naught plus h minus f of x naught all divided by h as h approaches 0. And we're evaluating this limit at the point 3, 9, so our value x naught, that's equal to 3. So we substitute that in, and we get the limit of 3 plus h squared minus 3 squared all over h as h approaches 0. When we multiply that out on the next line, we get the limit of h squared plus 6h plus 9 minus 9 all divided by h as h approaches 0. Now our plus 9 and our minus 9 cancel, giving us the limit of h squared plus 6h all divided by h as h approaches 0. And when we divide by h, we get the limit of h plus 6 as h approaches 0. Now at this point, we can evaluate that limit by substitution. We can replace the h with a 0. So our limit of h plus 6 as h approaches 0 is 0 plus 6, which is equal to 6. So we've just calculated that the slope of our curve y equals x squared at the point 3, 9 is equal to 6. So now that we have the slope, we want to substitute this value into our equation of a line. Y equals m into x minus x1 plus y1. We also have x1 is equal to 3 and y1 is equal to 9 because we're finding the equation of the line through the point 3, 9. So when we substitute those values in, we get y is equal to 6 into x minus 3 plus 9, which is equal to 6x minus 18 plus 9. And that evaluates to 6x minus 9. So we've just worked out that the equation for the tangent line to the curve, y equals x squared, through the point 3, 9 is y is equal to 6x minus 9. Now, we can use the differentiation rules to find the slope of the curve more efficiently. Using the power rule, the slope m of y is equal to the derivative of x squared with respect to x. And using the power rule, that's equal to 2x. So at the point 3, 9, our value of x is equal to 3. So at that point 3, 9, our slope is going to be equal to 2x, which is 2 multiplied by 3, which is equal to 6. So here we've just calculated the slope using the differentiation rules, and we've done it in a lot easier way. And now we can calculate the equation of the tangent line in exactly the same way. We use the equation of the line, y equals m into x minus x1 plus y1, and we have all the same values. Slope is equal to 6, x1 is 3, y1 is 9. We substitute them in the same way, and we get the equation of the line, y equals 6x minus 9. So you can see here that by using the power rule, that differentiation rule, we can complete the same task, but in an easier way with less work. Really useful to see and to remember. So now I'm going to talk about the second derivative. Up until now, we've been calculating the derivative of various functions. But we can also calculate the derivative of a calculated derivative. Here below, we have y is equal to 16t squared. So if we wanted to calculate the derivative of y with respect to t, that derivative, dy dt, that's equal to 32t, using the power rule and the constant multiple rule. Well, we can also calculate the derivative of dy dt. And that's expressed in the line below as d squared y dt squared. And we evaluate that using the constant multiple rule and the power rule, and we get that it's equal to 32. So our dy dt was our rate of change of y with respect to t, and our d squared y dt squared is our rate of change of our rate of change. So we can express this using more than one notation. They both describe the same thing. On the left hand side, we've just shown a derivative and a second derivative evaluated using the Leibniz notation. Now on the right hand side, we're displaying exactly the same thing, but we're writing it in a different way. So we're using what's called a prime notation. So we start off with y is equal to 16t squared. Our derivative y prime is equal to 32t. Calculated in the same way, but this is just another way that we can write it. Our second derivative is referred to as y double prime in this notation, and it's equal to 32, and it's calculated the same way. So when we continue to the application section of the Calculus Guide video series, we're going to see a practical example of finding the rate of change of a rate of change, finding a second derivative. So thank you for your time and for watching this video. See you at the next video.